Now, we are going to take up one more concept, which is shear stress and shear strain. So what is shear stress here? If you are considering that figure A and also figure B, you can see here, when a body or a section is subjected to two equal and opposite forces. So when a body or a section, so this is a section having two plates, having a rivet between the two plates, is subjected to two equal, that is P and also P here, equal and opposite forces acting parallel or tangential across the resisting section, that is figure A, and tends to shear off the body across the cross section. So that means across the cross section it is shearing off. That means this pin top portion will be separated from the bottom portion, which is as shown in the figure B. Then the force is called shear force and the stress induced is called shear stress. The corresponding strain is known as the shear strain. So here, if you take that as the concept, here if you are considering a member of a rectangular cross section of A, B, C and D, having a shear force which is applied at the top at P towards the right side. So at the bottom side also you can see that the magnitude will be equal to P but in opposite direction, so that the body is in equilibrium condition. Consider a section XX which is parallel to the applied force as shown in figure A. The lower part will be in equilibrium if the resisting force P dash will be equal to the applied force P, which is as shown in figure B. So that means if you are considering the section, here we are considering the lower part in equilibrium. So when they consider the section, so this will going to be first part and this will going to be the second part. That means AB we are applied with the applied force P. In order to keep the AB in equilibrium, AB and this XX in equilibrium condition, you should have a resisting force which is acting in a direction opposite to this applied force P. So that resisting force will be moving towards the right side, wherein the resisting force P dash. Now the body which is in figure B shown is in equilibrium condition. Similarly, if you are considering the upper part is in equilibrium condition. Now if you want to take the upper part, if the resisting force P dash will be equal to applied force capital P and is shown in figure C. So here, now this body is in equilibrium condition because when the force is applied at the top, which is C, which is CD, and the force is applied capital P towards the right side, the body will tend to move in the right direction. But in order to keep this body in equilibrium condition, you have to have a force which is equal to, the magnitude should be equal to the applied force, which is P. So that force is called as the resisting force, which will be equal to P dash. And then since the magnitude of both P and P dash are equal, therefore the resisting force P dash will be equal to applied force P, which is as shown in figure C. This resistance is known as the shear resistance, and the shear resistance per unit area is known as the shear stress. Now let P is the applied tangential force and P dash is the shear resistance. Then A is the shear area. Then what is shear stress? That is shear resistance by shear area, which is applied tangential force by shear area, which is P by A. P dash will be equal to P. Shear resistance by shear area, which is numerically equal to P dash by A, as P dash is equal to P, therefore P by A. So applied, what is P? Applied tangential force divided by shear area is going to give you the shear stress. So here, when you are trying to define what is the shear stress, here you have a member ABCD applied with the shear force P and with H as the height and length of this L. Then since AB is fixed and P is the applied force at the top, so point C and D will going to be displaced to C1 and D1, whose magnitude will be equal to delta L. The deformation will be delta L, and And here also on this area, which will going to be delta L. And the angle made by this will be phi, which is phi here, as shown in the figure B. So figure A shows the rectangular block of height h and length L and unit width is subjected to shear force P on the top and bottom faces. As the bottom face is fixed, so what happens? The block deformed to AB C1 D1 due to the applied force or the shear force P, which is as shown in the figure B, which has been already explained. Now, let the transverse or horizontal displacement at the upper face be delta L. So height of the block is h and the shear strain be phi. So what is shear strain? That is transverse displacement by distance between the upper and lower faces. What is the transverse displacement? CC1 or DD1 by AD, which is equal to delta L by h. So that will be shear strain phi will be equal to delta L by h. So as phi is small, tan phi is equal to phi. Therefore, so that is how you will be able to get the shear strain. So what is the linear strain or the longitudinal strain? When a body is subjected to an axial tensile force, when a body is subjected to an axial tensile force or compressive load, there will be an axial deformation along the length of the body. Longitudinal or linear strain is defined as the ratio of length axial deformation to the original length of the body. So what happens when the body, which is initial position is L, when it is applied with the tensile force, the body will going to get elongate. What is the cross section of the area initially, which is B by T? As the length is increased, so it will going to be, as the tensile force is applied or the axial force is applied, then the member will going to be elongated. So that means it will, along the length, it will going to increase. Correspondingly, it will going to reduce us in the cross section, which is B minus delta B and T minus delta T, which is as shown in the side view. So what is the final length? The final length will be equal to L plus delta L. And what is the final area? That is minus B minus delta B and T minus delta T across the cross section. It is also defined as change in length per unit length in the direction of the applied load. So let L be the original length of the body and delta L is change in length or deformation in length. And P is the axial load. It is tensile or compressive. So what is the linear or longitudinal strain? That is change in length by the original length. What is change in length? Delta L by original length is L. So delta L by L is the linear or longitudinal strain. So what is the lateral strain? Lateral strain is the same figure wherein here it will be reduced by B minus delta B and T minus delta T. So when a body is subjected to an axial load, it undergoes deformation in the direction of load and perpendicular to the direction of load. So which is the perpendicular to the direction? It undergoes deformation in the direction of load means it is along the length of the member, it will going to increase. And what happens to the load per direction? Perpendicular to the direction of the load. Correspondingly, the area of cross section will going to decrease, which is as shown in the dotted line. Initially, the position was B and T. As the axial member is elongates the body as the axial force is applied. So the length of the body will going to elongate. So therefore, in order to keep the volume of the member will going to be same, so it will reduces the area of cross section. The reduction in cross sectional area is B minus delta B and T minus delta T, which is as shown by the cross section with a dotted line in the side view. So that is the perpendicular to the direction of load. Which is the perpendicular to the direction of load? The perpendicular to the direction of load is this cross section, which is shown in the dotted line in the side view. So consider a rectangular bar of length L, width B and thickness T. subjected to an axial load, which is as shown in the figure. Due to application of this load, the length of the bar will increase while the breadth and thickness will decrease. If the load is compressive, what happens? The length will decrease, the area of cross section, that is breadth and thickness, will increase. So the strain in the direction of applied load is known as the longitudinal strain, and the strain at the right angles to the or perpendicular with the direction of load will be the lateral strain. So let delta L will be equal to increase in length. So what is the increase in length? L plus delta L minus L. So that will be equal to delta L. What is delta B? Decrease in width. B minus delta B minus delta B. So delta B will be the decrease in width. Delta T, decrease in thickness. That is T minus delta T. So delta T. So L will be the original length, B is the original width, and T is the original thickness. So what is now linear or longitudinal strain? That is delta L by L. So lateral strain is delta B, change in lateral dimension by the original dimension, which is delta B by B or delta T by T. So this is how you will be able to define the longitudinal strain, longitudinal stress, lateral longitudinal strain, and also the shear strain. Thank you.